This conference will now be recorded.
Hello students, we're back with the second lecture on wave optics. So today we are going to show you how we can explain the phenomena of reflection of light and refraction of light using wave theory, basically using Huygen's construction, geometrical construction, or Huygen's principle, which is based on wave theory. So as we have discussed in the introductory class, that wave theory is a better theory. Okay, so any better theory must be able to explain the phenomena which were being explained with the old theory or old concept. So here wave theory is actually replacing the ray optics. Okay, ray optics or ray concept of light. So wave theory must be able to explain the phenomena of reflection, refraction, dispersion, etc., which were being explained with the ray optics. Okay, so here, before I go to explain you this reflection and refraction based on Huygens principle, let me just recap very briefly about what is Huygens construction, geometrical constructions, or Huygens principle. See, if you remember, we had discussed that according to Huygens principle, each point on a wavefront will act as secondary source. Okay, each point on, so I'll just write, so first point was each point, sorry, each point on the wavefront acts as a new source of or a source of new disturbance, a source of new disturbances. Okay, new disturbances. So these disturbances are called waves or wavelets. Okay, new disturbances are called wavelets. All right, the second thing was the secondary wavelets will progress or propagate with the speed of light in the forward direction always. Okay, speed of light. Okay, speed of light, it will spread out in all directions. It says, we'll see, by the way, in the backward direction there is no flow or no propagation of the wavefront. We had shown you that day 1 minus cos of theta, right? This is what we had seen, or 1 plus cos of theta. So when theta is pi, then it will be 0. So the intensity of the light or secondary light or the wavefronts is actually proportional to 1 plus cos of theta. That is what we had discussed in the last class. I'm not going to repeat that. So just the Huygens construction I am just mentioning. And the third point is that if we know the position at any instant of time, if we know the position of wavefront, we can, okay, if we know position at any instant, then we can find the position and shape of the wavefront at any later time, okay, at any later instant of time. So that I'm not writing here because of less space. So I'll just repeat, each point on the wavefront acts as a source of new disturbances which are called wavelets, and these wavelets will be propagating with the speed of light. And if we know the position of the wavefront at any instant of time, then we can find out the position and the shape of the wavefront at any later instant of time. See, we had taken these examples. See, whether you take a plain wavefront or you can take some surface of a curved wavefront or maybe spherical wavefront, anything you can take. You look, for both cases, both the figures, you look, suppose at any instant of time the position of a plane wavefront is AB. At this position you can see that. So this figure I'm talking about. So AB at any instant of time it is AB. And also you can see similarly in this curved wavefront also, this is a part of wavefront you say, and so this AB, this is a part of wavefront. At any instant of time t, you know the position here, AB position. Okay. Now we know according to Huygens principle, each point, okay, each point will act as a source of secondary wavelets. That means it will produce secondary wavelets, and as we know, point sources will produce spherical wavefront, right? So you can, suppose we want to know the position and the shape of the wavefront at any later instant delta t, at any later instant delta t, then we have to draw, see, we have to draw, suppose from this point A, see there are few points we have selected on AB here in the plane wavefront, even at the curved wavefront also you see here A, B, C, D, E, we have chosen some points. So those points we are just taking as representative points, while other points also will produce such wavefronts, okay, so new wavelets. So A, see how to do the construction, geometrical construction. See, you have to actually draw a sphere, or here actually you are drawing circle, but we should say this is sphere. But what will be the radius of the sphere? This sphere, because we want to see the wavefront at later instant delta t, and wavefront will move with speed c. So we have to actually draw a sphere like this with a radius of c delta t, as you see in the figure, both cases. Okay, in both the cases you can see that we want to see the shape and the position of the new wavefront at any later instant delta t. Okay, so that's why, see, each sphere will be of radius c delta t. So this is what we have drawn. You can see that. So we have drawn small spheres, and thereafter what you have to do, Then you look, we have to draw a common surface, tangential surface to all the spheres, and you look that a prime b prime is that common tangential surface. So what I have said, you have to draw the spheres of radius c del t from all the points. Actually all the spheres will be of same radius, because you know, like this these new wavelets are in phase. Wavefront means they are all in phase. Okay, so they don't have any time lag here, so all of them will have the same radii. They are just moving together. So small spheres you have to draw, and you can draw a common tangential surface a prime b prime, okay, in the front side, or in the, this is called forward envelope. This is called forward envelope. So this is what is taken as the position, and also the shape of the wavefront you get here is plane, because the AB is the plane wavefront, so you get plane wavefront at later instant also. Okay, this is actually taken forward envelope. Forward envelope, sorry, envelope is the wavefront, new wavefront. Okay, so here in this case also this is the new wavefront, new wavefront. But why we have not taken a double prime or b double prime? Because we have seen the intensity of the light or the wave in the backward direction is proportional to this, and when the angle between the ray and this position where we are seeing the wavefront, look, this ray is going this way, or the direction of the wavefront, at least we are taking this direction, forward direction, and this is actually we are looking, so this angle will be phi, so that will make you see, this will make you 0. Okay, this particular factor 0 if you take theta is equal to pi. So we have discussed that already. So now why I have recapitulated this is that this is what we are going to use to explain the phenomenon of reflection and also the phenomenon of refraction of light. Okay, so wave theory, this is actually based on wave theory. Okay, the Huygens principle is based on wave theory. Okay, so let us go to the next page or next topic, that is reflection. So look here, you might be very much confused with this figure, but I'll just step by step explain so that you get the essence of it. See, we are going to see, you know, laws of reflection. We are just verifying laws of reflection, laws of refraction using wave theory, and very like more specifically using Huygens constructions. Okay, so here anyway you do this analysis, ultimately you should get angle of incidence is equal to angle of reflection. Okay, and incident ray, normal, and reflected ray must be in plane. Okay, must be in plane. So these are 2 points we have to actually show from this Huygens construction. Okay, so look, I'm taking at any instant of time, at any instant of time, at any instant, there is an incident wavefront, that is AB. See this AB plane wavefront we have taken here. So this is plane wavefront. Okay, this is incident wavefront. It incident on the reflecting plane AMN. AMN is the reflecting plane. you can see that reflecting plane is Mn. And you see, when this wavefront, see AB is the wavefront, so here I'll write AB, incident wavefront. See, this wavefront, actually it is kind of obliquely incident on the reflecting plane Mn. That means what? See, the wavefront will touch or meet the reflecting surface Mn at A first, right? First, the incident ray will meet or reach the reflecting plane Mn at this point A, right? So as you see from the figure, see this ray or this side of the wavefront is already touching or already it has reached to the reflecting plane, and this B point then it will reach the reflecting surface later, and where it will meet at C. So that is what we have understood. What we have so far understood, we have understood that AB is incident of front at an instant of time. This is the case that the wavefront has touched or reached at the point A on the reflecting surface Mn, right? And at later point, this B will also touch this reflecting plane because it is progressing towards C, right? So this is the case. Now, what happens by the time wavefront comes from, see, this point B reaches to C, by the point wavefront or the light wave reaches from B to C, there will be secondary wavelets produced by this AB wavefront, right? See, this AB wavefront, see, there are A points, B points here, and C point, and in intermediate many points will be there, right, on the wavefront. And each wavefront will actually, each point on the wavefront will actually produce secondary wavelets, as we have seen, and that's why these sources are called also secondary sources. So these secondary sources will produce wavefronts, right? I'm just taking the point A on this wavefront, which will produce a spherical wavefront. Okay, spherical wavefront. Suppose I'm seeing just after touching this. So after, okay, we are trying to locate the new position of the wavefront after, okay, t time after the wavefront reaches at A. Okay, what does this mean? See, when the wavefront AB reaches to the plane surface or reflecting surface at A, after that t time, okay, we are just looking for t time. So after t time, what will be, or after t second, let us say t second, after t second, what will be the new position and shape of the wavefront? So that is what we are just trying to look at here. See, we are just, see, just after reaching this wavefront, reaching at this point A, we are just counting t seconds. So you look, as I said, the wavefront will touch at A first, then B point will touch, or B point will reach up to C. Okay, But by the time, see, if I say that t time is taken by this b, okay, t time is taken by b to go up to c. So by the time this b reaches here, this point A will actually produce spherical wavelets, okay, spherical wavelets, and that spherical wavelet will actually reach, see, it will reach from here like this. Say this wavelet will reach up to this point E, up to this point E. By the time B goes to C, see the secondary wavelets will, the spherical wavefront, see this is part of spherical wavefront like this, it will reach up to E, isn't it? Look, I think I have, I'm sorry. So see, by the time B goes to here, secondary wavelets produced by this point A will reach up to this E point. So we can say that this AE is equal to BC, because if the speed of light in this medium is, say it is some B, then both are actually traveling time t, so BT, both are actually the same. Okay, this distance AE and BC will be same because they have the same, this is the part of wavefront, this is the point of wavefront, so wave will travel with C, okay, or let us say this is C itself, it is, if it is in vacuum then it is C, and they are traveling for same time t, so their distance will be same. Now I have to actually prove this angle of incidence equal to angle of refraction. All right, so here you look, if we draw a tangent to this spherical wavefront produced by this, like secondary wave, let's here, so if we draw the tangent, so this tangent will touch here, you can actually understand the time. By the time this goes here, there will be wavefront like here, one wavefront will be like this, okay, okay. So if we take a common tangent at this particular position, if we take a common tangent, you look, I'm taking common tangent, okay, common tangent, I'll just try to make it a little better. See, there will be a part of wavefront here also, I'm sorry, like this. Here one spherical wavefront will reach from B to C. So if we take a common tangent on this wavefront, okay, and on this wavefront we'll get a surface. See EC, this is a plane surface, and it is actually the reflected wavefront. Okay, this is itself is reflected wavefront, that you can understand, reflected wavefront, reflected wavefront. Now see, we have to show somehow. See, the reflected wavefront is making an angle, this R, okay, isn't it? It is making an angle R, and this is incident wavefront making an angle I. So this we can take as incident wavefront, and this we can take as, sorry, incident angle, this we can take as reflected angle, okay, or angle of reflection. So we have to show these two angles are same, okay. So to show that, let us take these two triangles. What are those? Two triangles. One is A, B, and C. Triangle ABC, and triangle AEC. See, from here, what we get from this triangle? See, from here we get ABC, this BC. See, this is actually from this both triangle. What a common look we see. See, we get AE is equal to BC. Okay, and this the AC is actually common to both the triangle, isn't it? Common to all. Okay, both the triangle. AC is common. So I have got two equal sides, and then if I get one angle equal, then we can say these triangles as similar triangle. Then the third, like other angle also will be equal to each other. That is what we are going to now do. So we have to show this ABC triangle and AEC triangle to be similar triangle. So I have got two sides of the triangles are equal. Now one angle, look this angle, this is actually tangent to, right? Tangent to this spherical. See, any tangent makes sure this radius 90 degrees, isn't it? So this is kind of, so this is, you look, this is the ray. Ray is always actually perpendicular to the wavefront. So AE, and this is the ray. So this, then this angle must be 90 degree, isn't it? Because it is spherical surface, spherical wavefront, and this as act as radius. Okay. So AE, this is actually mechanical. So this angle is 90 degree. So what you can write here, AEC is 90 degree. What about this ABC? So this angle also will be 90 degree because this is, see, this is ray, kind of ray, and this is actually wavefront AB. Okay, so AC we can take as a ray, and AB we can take as a wavefront. And see, wavefront and the ray will be always perpendicular to each other. So this B point ABC also will be 90 degree. ABC will be 90 degree. Angle ABC will be 90 degree. All right. So we have got two sides, this side and this side of these two triangles. And look, this angle and here this angle, these are equal to each other. So we can say that these two triangles ABC and AC are actually similar triangle. So from these two, we can conclude that triangle ABC similar triangle, actually similar. I hope it is given like this. So both will be similar triangle is written like this, AEC. Okay, so both are similar triangle. So if they are similar triangle, we can say I is equal to R. Okay, I is equal to R. We can say angle I is equal to R. Okay, so this is what we had to mainly explain, whether angle of incidence and angle of reflection are same or not. So this is actually law of reflection, and this we had to verify. We had to verify with wave theory. Okay. Now look here, the incident ray, and you can say this is the reflected ray. This and the perpendicular this A. Suppose this is the perpendicular. Okay, the normal to the plane. So if these are, so you can see these are all actually in the same plane. So this is how we can explain the laws of reflection. Now we'll just go to the laws of refraction. So it is actually purely Huygen's construction which we have used here, and later on we'll actually learn very interesting things in this chapter, like interference, diffraction, etc. When we'll learn those things, those will be actually fascinating and very much interesting. So these are just old stuff we are just verifying here with the wave theory. Okay, now let us go to the refraction part. So here also similar thing, what we will do, we'll take a point on the wavefront, okay, and we'll see whether it is sending some waves and how much time it takes, etc. We'll analyze. or how much distance it will travel in a particular instant of time, where we are just trying to understand the position and shape. See, suppose in this case we want to locate we want to locate the refracted wavefront after tau. This is the time. Okay, according to the figure, you look, the incident wavefront is AB. Okay, this incident wavefront is actually all the way coming and getting refracted. This wavefront is getting refracted at the interface of this interface P prime, which is actually separating two medium having refractive index, different refractive index. Maybe this as mu1, this is mu2. Okay, so the medium P and P prime is separating these two medium. Okay, so this, okay, so P prime is the interface. Okay, and since these two mediums have different refractive index, so they must be having different speed in the different medium. So because this is one medium, suppose this is medium 1, this is some medium 2. Okay, now see, when the wavefront, in this case also, when the wavefront reaches at point A on the interface, by the time this B point will not reach. Actually, I'm trying to say that this wavefront AB will touch or reach the interface first, and then wavefront will reach from B to C later. Okay, so what happens? See, wavefront after reaching at this point A on the interface, this point A on the wavefront will actually produce. Obviously, it is producing every time, but we are just looking that particular instant after which it is like after which we want to look the shape and all. So look, just after reaching the interface, wavefront from A, new wavefront or wavelets will move up to this point E. By the time, suppose I'm just now I have written that after time tau, after means after reaching at point A, we are just waiting for tau time. Okay, tau time, and after that we are just going to see the shape and size. Okay, so by the time this B point reaches to C, a secondary wavelet will actually move in the other medium, in the second medium, up to E. If it is not clear, if my language is not clear, I'll just restate this. See, we are just trying to look the shape and size after tau time of reaching this wavefront AB at A point. Okay, on this interface. So just after reaching here, I'm just taking one wavelet which is moving in the second medium from this A point till E, and by that time wavefront from B to C, it like the incident wavefront will reach this interface from B to C by that time tau. Okay, that is what is the physics over here. So by the time this B reaches to C, there will be secondary wavelets which will be reaching to E in the second medium. That means, that means this AE, obviously this AE distance, now this AE distance and this BC distance will not be equal. Why? Because time is same, but the velocities, see V1 will be greater than V2 because this is air, say this is some denser medium. In the denser medium, light will not move faster, okay? All right. All right. So in this case, what is happening? See, AE will write it. We'll write here. What are the things we are getting? AE is V1 tau. What about BC? No, this is V2 tau. BC is actually V1 tau. Okay, because tau second, after tau second, what will be the distance traveled? Okay, that is V1 tau. V is the speed, and this is uniform speed. And in the medium, second medium, the speed is V2. Okay, so V2 into tau. So here we are just taking these triangles ABC, ABC, and AEC. See here we are actually trying to prove the laws of refraction. So what we have to do? We have to actually prove Snell's law. Snell's law here also. With this geometrical construction, we have to prove this Snell's law. Snell's law means what? Sine I by sine R is mu1 mu2, sorry, this will be mu2 by mu1. Okay, because n1 sine 1 is equal to mu1 sine 1 sine I is equal to mu2 sine R. So this we have to prove actually. Okay, this we have to prove. So how to do that? It is not very difficult. See from this figure, see this is the angle I here. This is the angle I. Okay, you might be thinking, how do we get that? See, it is not very difficult to get. See, this is the ray A prime A. This ray is incident on this. This is the normal to the surface. So this is the angle of incidence, right? We have to find out what is the angle here, isn't it? This I, whether it is really I. See, this particular angle is 90 degree. Okay, this particular angle is 90 degree, and say this angle must be 90 degree. So let us say this angle is x. Okay, or let me tell you this must be 90 degree. Okay, so this must be 90 minus I. Okay, because this is the ray, this is the wavefront, so this is 90 minus I. So again we know this angle also will be 90 degree, so this must be I, so that this plus this particular angle plus this angle will make it 90 degree. So that's why it is I. A simple geometry from your 10th standard. Okay, so we want to write sine I. What is sine I here? Sine BAC. Sine I means what? Sin I means sine of angle BAC. And sin R is this angle ECA or ESC, whatever you can write, sine of angle, let us say ACE. Okay. So sine of BAC, look what we write here. This is a right angle triangle. You can see that this is actually hypotenuse. This is base. This is perpendicular. Okay. So we can write sine BAC. Sine BAC means this angle. This angle. So we can write. So on the right hand side, sine BAC means what? BAC. BAC. This. So we have to write sine means perpendicular by hypotenuse. Perpendicular is what? Yeah, perpendicular is this BC. BC by AC. So this is sine BAC. And then what is this sine ACE? Sine ACE, this angle will be actually AE by AC. Since this AC are common to each, so I can write sine I by sine R. Sine R is equal to BC by AE. So BC by AE. What is BC then? I'm just actually going this way. Okay, let me just go to the next page. That will make things better or little clean. So sine I by sine R is equal to, I'm sorry, sine I by sine R or sine BAC by sine ACE. That is what I have written, I think. ACE. Let me see. Yes, ACE. So where we have seen this is actually sine I by sine R. This is equal to BC divided by AC. BC means V1 tau. AC will cancel each other. Here you will get ACE. Sine of ACE means AE by AC. So this AE will be actually AC will cancel each other, that I have shown you. AE is actually V2 into tau. Okay. All right. So tau get cancelled. So this could be actually written. See if I just write C by V1 okay, for the time being, let us keep it here. Then we have to show this V1 by V2 is mu2 by mu1. That is what we have to show. Okay. Now see, as the speed of light, as the speed of light as the speed of light V1 and V2 are different in the to medium, different in to medium, to media. We should write to media. To media. See, if I say the wavelength of these two media are W1, lambda 1, lambda 2. Let us say this has wavelength lambda 1, this has wavelength lambda 2. Okay. Then we know for a wave, V is equal to lambda into nu. Okay. Nu into lambda. Right? So we can write it here, the nu lambda 1 . Okay, so we get, see, from here ultimately we get lambda 1 by lambda 2. Okay, and see, in this case, one thing you need to note that okay, so we need to note that frequency always will be the same. Frequency doesn't change medium to medium. Okay, frequency of light will not change medium to medium. It will actually be the same in the all medium. So this nu can be cancelled out. So then what you get, this is lambda 1 by lambda 2, and again we knew that v1 by v2. Okay, so look, actually what we can do, we can make this one to write somehow in terms of, okay, so if we write this c by v1, okay, so we have to write here also c by v2. I think just a minute, this I could write, I just divide by c, divide by c. Okay, then this will be c 1 over mu1, and here it will be 1 over mu2. Okay, that means mu2 by mu1. So if we write in terms of relative one, so mu 2 1. So this is what we get. So sin I by sin r is equal to mu2 by mu1. So you can see mu1 sin I, mu2 sin r. This is Snell's law. Okay, this is Snell's law. So this is what we have actually proved here. So wavelength of medium is directly proportional to, see here, always this thing you have to remember, this v is speed of light in any medium is directly proportional to wavelength and inversely proportional to the refractive index. Okay, so inversely proportional to the refractive index. This is what we have to remember. Okay, so this is how we can actually prove the laws of reflection and refraction. And see, another part we have just remaining. See this, if we just take this is incident, this is suppose plane wave. So okay, so it is incident one, reflected one is this, and perpendicular is actually, you can say, the plane itself is the perpendicular. And in this case you can just see that this a prime, a, this is perpendicular, and this p prime is the interface. So all are actually refracted ray is this one. You can see ae is the refracted ray. So refracted ray is this ae, incident ray is a prime a, incident ray, this is incident ray. And this is reflected ray, sorry, refracted ray. Refracted means just pass through the medium. Refracted ray. Okay, so the incident ray, the reflected ray, refracted ray, perpendicular, and the interface, actually perpendicular or normal to the interface. See, this is incident ray, this is refracted ray, and normal to that interface is in the same plane. So that is what we had to discuss there. Okay, so look, in, see, we have already seen this. Now see, in case of, in case of uh, suppose in case of lens, how do we explain? See, suppose this is convex lens. If we just go for plane, see, sorry, if we go for just ray optics, any parallel ray incident will actually meet at a focus, right? I'm sorry. Okay, so after refraction, the meets at some point, right? How do we explain this? So in this case, the central part, you look the central part and this part, edge of the this lens. The central part is most thicker, right? Thickest part of this, and this is actually thinner, isn't it? So if I take the plane wavefront like this, okay, plane wavefront goes like this, reaches here, and then it actually transmit through the wavefront, and sorry, this transmit from this through this lens. And you look, see, each point on this wavefront will produce spherical wavefront, right? Secondary wavefront like this they will produce, and this secondary wavelets will move and pass through here. So while passing through, look what happens. So the wavefront here, they will pass easily, or they will pass, and by the time they pass, the wavefront which are passing through the middle will not be able to pass, isn't it? So these will have actually faster speed than the speed which are passing through the medium, sorry, thicker medium. Okay, so this part, so in the medium, it is actually, by the time this ray just comes out of the material of this lens, the wavefront which was passing directly like this, that has to actually travel greater path. Okay, greater path. So greater thickness means greater path. So then marginal, okay, so that's why the emerging wavefront will be how how does it look like? Emergent wavefront. See, emergent wavefront, this will move faster. As I said, they will move faster. See, it will look like this here. So this part will move by the time the wavefronts from passes through the middle point and come out here. The wavefronts which are passing through the edge will actually pass through and also move. Okay, so this is how you see here. This will be actually the wavefront. After, see, plane wavefront, after passing through the lanes, it will actually see become a curve, right? So that's why you can say this, the ray are actually converging here. Okay, so rays are converging here. In case of mirror also we can show, and see, in case of dispersion through prism or refraction by prism, see, this part is thinner, this part is thicker, this part is further thicker, like that, isn't it? So when a plane wavefront passes through this prism, so middle point, so this point will actually move faster. These points will move faster than the middle point, so they will actually reach so this will be something like this. Okay, so this point will be moving faster than, see, this will move greater distance than this one, then this one, then this one, then this one. Okay, because this is actually moving through the thinner region, okay, with the same speed. So that's why this will move up to here. All right, so plane or say this is AB, this is AB, this becomes like this. It is actually become, that depends on the prism, okay, how it is to be kept and all. So with this, actually we have completed this part, today's part, this reflection and refraction phenomena using Huygen's principle. So next day what we'll do, so next class, in next class we'll discuss about interference of light, okay, or superposition of light. In the next class we will learn superposition principle. We have been learning this, actually we have been discussing this superposition principle in case of vector, in case of sound wave. Okay, so here also we'll discuss a little bit, and then we'll see basically interference, what is called interference, we'll see, and we'll try to okay, so few more things we'll do here, actually coherent sources, etc. Coherent sources, coherent source, non-coherent sources, etc. are there. Those things we'll discuss. Then we'll go for the interference of light, etc. Okay, so thank you for your patience. Bye for today.